Hello dear students, welcome to the lecture series on Verilog HDL. I am Professor Vikas Balakai. This is module number 1, lecture number 3. Now, a few of the topics that were covered in the previous lecture where we tried to cover up the typical HDL design flow, or what we know as IC design flow, or the entire application specific integrated circuit design flow, and we figured out what are the level of design flow that happens right from the behavioral modeling or right from the design specification till the manufacturing of an IC. Then we also figured what is the importance of Y graph or Y chart, and how the three different levels or three different ways to map the different coding aspect into an Y graph. That also we saw. Now, the topics what we are going to learn in today's lecture are what is the importance of HDL, that is hardware description language, and we'll also see the levels of abstraction in Verilog. I'll tell you what exactly abstraction mean in my subsequent slides. Then we'll see what are the different design methodologies and hierarchical modeling concepts that are available. So we'll be dealing with these concepts in today's lecture. And once a student understands all these concepts, he'll be in a position to describe different levels of abstraction in Verilog. Again, I'll just tell you what exactly is abstraction level in the subsequent slides, which we are going to discuss today. Fine. What exactly HDL plays? So what is the importance of HDL in today's era? Now HDLs have many advantages as compared to the traditional schematic based design. Now the first one being the abstract level design. Now what exactly we mean by when I say an abstract level design? So it only means that designs can be described at very low level using the hardware description languages. Not necessarily that one has to describe the design at a very higher level. One has to can define the level, or one can be writing the code at very basic level. In the sense, the we can write the code even at a gate level, or to some extent even we can write the code at the transistor level. So that is the level of abstraction. That is the level of design feasibility that HDLs provide. Then no restriction on fabrication technology, which means designers can write their RTL description without choosing any specific fabrication technology. That is, logic synthesis tools will automatically convert the design into whatever the fabrication technology that we are using. No need to worry about in which technology it is going to be fabricated. Our job is to just write a code. Let the technology that is used at the fabrication level will pick the program, and it will modify the program according to the technology that is being used at the fabrication level, or at the manufacturing level. So that is one of the again advantage of hardware description language. The third one is technology adaptation. Now, what exactly we mean by technology adaptation? Now, for example, if any new technology emerges, designers do not need to redesign their entire. They instead can simply input the RTL description to the logic synthesis tool and create new gate level netlist using the new fabrication technology. Like for example, I have written a particular full adder program, and I have generated the gate level netlist. That is gate level breakup of that entire full adder program. I have generated that netlist, and now I want to fabricate it in, let's say for example, XYZ technology. Now I'll provide this netlist to that XYZ technology. See, I'm deliberately not using any particular technology name, because as of now you are not completely aware of what exactly we mean by technology. So let's not get in depth into with respect to the technologies that are being present. Let's say there is an XYZ technology. Now I give this full adder netlist to that, and then they will convert that netlist into the IC. Now let's say tomorrow a new technology comes, then I need not to rewrite my program which will work for new technology. Rather, my netlist, whatever I have generated, I need to just regenerate the netlist for already written program. So that's what the technology adaptation that I was talking about. No need to write the entire program. You just need to regenerate the netlist. So program will be there as it is, according to the specification that are available at the fabrication center. That's how I can say that technology changes. Well, whenever the technology changes, only the netlist will change, not the entire program. The fourth one is optimization in new technology. What exactly this means? When I say optimization in the new technology, it means the logic synthesis tools optimize the circuit in area and timing for the new technology. So we need not to worry much about what the new technology will do with respect to the existing code. The timing analysis, the synthesis, and the mapping, everything will be taken care by the new technology whenever we are changing from one technology to another technology, and it will try to optimize the existing code according to the new technology. The sorry, the next one is early functional verification. Now, what this means? Now, functional verification of the design can be done early in the design cycle. Like for example, I need not to wait until my entire design process is over. Like for example, I am designing a full adder, and I need not to wait until that entire full adder design is designed completely. I can functionally verify the full adder the moment I design AND gate, the moment I design an XOR gate, the moment I design an half adder. So earlier the functional verification, the more benefits will be there for your entire process, because once we complete the entire design and then we want to verify this circuit, and if there is some fault or if there is some error that is coming out, then I need to change the entire process or entire design. Rather than that, as and when you do or write a program, you check for the functional verification. So that one feasibility or advantage is provided by all the hardware description languages. The next one is reduced design cycle time. So what does this mean? Now, because I am verifying my content at the very beginning of my design cycle or design stage, that also mean that the entire design process time will also be reduced, because once I design individual blocks, and when they are verified at that level only, like for example, if I take a full header, it requires two half adders. Now, the moment I build the half adders, if I verify the entire half adders then and there itself, and then once I club them together and generate a full adder, now if I verify the full adder circuit, then I won't be getting, or the chances of getting an error or a fault will be very, very minimal, and hence I can say that the entire design cycle time has been reduced drastically. And finally, the hardware description languages are very simple to look, because they come with a textual description and make it very easier to understand and to code in any platform. So this is how the HDLs have many advantages as compared to traditional schematic design based programs, and this is how the importance of HDL languages have been portrayed. Now, what has made the Verilog HDL specifically? See, I was talking about here the general hardware description languages, which is applicable to Verilog as well. Now, here, let me give you a glimpse of what has made the Verilog language to be more popular among all the designers. Now, Verilog HDL has evolved as one of the standard hardware description languages over the years, because the nature or the kind of flexibility that it offers is very beneficial for the hardware design, and it is not very rigid, rather it is very simple to understand, and it is a very general purpose hardware description language which can be utilized and used by any of the engineer or any of the designer. And the third reason why the popularity of Verilog HDL is increasing day by day is because the syntax of this Verilog HDL is very, very similar to a popular C programming language, and hence that makes them uh, moving from one software domain to hardware domain in a very easy manner. And designers with C programming experience will definitely find it very easy to learn Verilog HDL when it comes to learning the hardware description languages. And the main advantage or the main popularity or the main reason why the Verilog is getting more popular nowadays is because it allows different levels of abstraction to be mixed in the same model. Now I'll just brief you in my next slide what exactly we mean by abstraction and what exactly we mean by mixing. But as of now, you just remember this one. And then this is one language which has, with all these features, has made it as a language of choice for all the designers, and hence that's how this particular Verilog HDL has become very very popular among all the designers. Fine. So let's look into what are the trends that are present in the HDL. We'll just quickly glance over the 10 trends. Now I'll just glimpse the entire thing, whatever that is shown in this particular slide. Now formal verification techniques are becoming very famous nowadays, wherein we can club some mathematical techniques to verify the correctness of any Verilog HDL programs. So that will enhanced weightage whenever we try to verify any particular programming aspect, because the moment I include mathematical aspects into any of my programming language, then verification will be very very rigid, and it will be very very firm, and there will be no scope of going wrong in any kind of verification steps. So that's where this entire verification process and mixed design mode and bottom up and top down methodology, I'll just brief you about all those things, and then possibly at the end we can again come back to the trends in HDL. There we can get a clear glimpse of how, why, or what are the different trends that are available in HDLs. Fine. So let's move into something called as uh, something what is known as levels of abstraction in Verilog HDL. I was talking about this abstraction level. So what exactly we mean by levels of abstraction? So I was discussing about the levels of abstraction in Verilog. Now basically there are 4 levels of abstraction. Now to put it in a very simple way or simple words, there are 4 ways to write a program in a simple language. So that's what we say at the level of abstraction. So what are those 4 ways or levels to write the program? One is to describe any given statement in its behavioral or algorithmic level, and that is known as behavioral description. The second one is to describe the way how the data is flowing from one end to other end. That's what we call it as a data flow level. The third one is to describe any given problem statement in terms of its logic gates and its interconnections, is known as gate level programming or gate level modeling. The last one, which is known as switch level, or sometimes it is also known as structural level, because or sometimes it is also known as transistor level. So switch level program is nothing but this is the lowest level of abstraction, wherein you try to describe a problem statement with the help of switches. And basically what do you mean by switches? What are the switches or the logical switches that we have? That those are nothing but your transistors. We try to program the given statement using the transistors, or to get into the exact structure of that particular device. Hence this particular level of program is known as switch level or structural level of programming. Now we'll try to have entire glimpse of how these 4 modeling works through a set of examples, but just we just remember there are 4 levels of abstractions or the ways to write program in Verilog HDL. Once we are done with this, and now how do I start to write the program? Now I told you there are 4 levels or 4 ways to write a program. That's fine, but how do I start? Now in order to understand this, we have basically 2 set of approaches, which we call it as hierarchical modeling. Now one is known as top-down design methodology, the other is known as bottom-up design methodology. Now on your left side you can see there's a top-down design methodology, because the arrow marks are shown from top to the bottom level, and the right side you have the bottom-up approach, wherein the arrow marks are shown from bottom to the top. Now in a simple language, I'll try to give it a very clear picture of what exactly they mean. Now top level or top down design methodology is nothing but, like for example, let's say I want to design a parallel ladder. Now this is my top level block. Now I don't know what are the contents that are going to be present in my internal, or what are the components that I am going to use in the parallel ladder, but right now I have a problem is my problem statement is I want to design a parallel ladder. Now that is my top level blocks. Now the thing is, I'll think what are the things or what are the components or what are the blocks that are available in my inside that top level block. Now if I say 4-bit parallel ladder, or let's take into a simple example of a full ladder. So that is my full ladder is my top level block, and if I just want to design the full ladder, what I need, basically I'll be requiring two half adders, an XOR gate, and an AND gate. So if I just get inside the top level block, what I can see two half adders. So those are your sub blocks. So start with main block, then design the sub blocks, and again inside those sub blocks, what is half adder? It is nothing but a combination of an XOR gate and AND gate. That become again one more sub block, and then what are the components that are present still inside? If at all any components are there, that will become one more sub block. So like that, if I just go from top to bottom, so that approach is known as top-down design methodology until I reach a leaf cell. Leaf cell is nothing but a structure or a component wherein further not be going inside, or that is the smallest level of component that is present inside in your entire programming aspect. So that's what is known as top-down design methodology. Now, what do we mean by bottom-up approach? It is exactly the opposite. Now, again, I'll take an example of a full ladder. So, I want to design a full ladder. That's my statement. Now, rather than first designing the full ladder structure and then getting inside, I'll start with the smallest components. Like for example, I require some transistors. Then I'll be building some logical gates. Then I'll be using those logical gates to form a half adder. Then I use those half adders to form a full adder. So I started from the smallest component and I reached the biggest block or the topmost block. So that is your bottom up approach. You start from the smallest component, you reach the largest component, that is bottom up. You start from largest component, you reach the smallest component, that is your top down. So these two design methodologies that are basically present in your entire very long coding aspect, and we'll be taking up very good examples in understanding these concepts. Is not that we'll be dealing with theories, we'll try to take many such examples and we'll try to deal with those things. Now to give a simple glimpse of what I have just told, this is a simple counter I have taken. Now here I have not mentioned any arrow mark. The arrow mark, if I give from top to bottom, it becomes top down approach. If I give the arrow mark the other way, it becomes bottom up approach. It is left to the user, whichever way he is convenient, he can design or he can adapt those methodology. Now I have used 4 flip-flops to form this counter. Now if I start from top to bottom, so I'll be looking into this entire counter. Let's say I want to design a 4-bit counter. Then what are the components that are required to build that counter? I require T flip-flops. So those will be my sub blocks. And again, in order to design a T flip-flops, what do I require? Here is my T flip-flop. As you can see, one D flip-flop and an inverter or NOT gate. So they become another sub block. So they are here. So again, inside this D flip-flop, are there any components that are present? If I want to further break it down, if I enter it, it is a combination of your NAND gates and NOR gates. So those again will become another sub blocks. So like this, I start from top and then I reach the bottom. The other way, bottom up approach could be the same thing. Now I'll be giving you NOT gate and a D flip flop, and I'll ask you to design a counter. Now what you'll do, you'll ask me the question, how many bit counter? 4-bit counter. Then what you'll do, you'll take 4 such T flip flops and arrange something like this. And then once you arrange it, you try to join the different T flip flops according to certain rules. And once you join it, you give the input and you get the output. If it is working like a counter, then that's it. You started from the smallest component and you arrived at the largest component. So that's how your entire process of a top-down and bottom-up approach works. So in the subsequent lecture, we'll try to basically in my next lecture, we'll try to take an example of a program, and we'll try to understand what exactly is your top-down and bottom-up approach, and what are the different levels of abstraction that we just saw, or that is what what are the different levels of programming, or how we can code any particular problem statement. That also we'll see in my subsequent lecture. So that is there in my next lecture. So this is it from today's lecture. Hope you have understood certain very interesting concepts with respect to Verilog HDL. So to summarize, basically we learned what are the different levels of abstractions that are present in this Verilog language. We also saw what are the what has made the Verilog language as most prominent language, what are the advantages of Verilog language, what are the key features of Verilog language. We also saw different hierarchical modeling, that is top-down approach and bottom-up approach. We saw that. And since all these concepts require recalling and understanding of certain facts, this entire lecture comes under level 2 of Bloom's taxonomy mapping, Bloom's taxonomy level, which maps to course outcome number 1. So that's it from today's lecture. Signing off from now, and we'll see in the next